So we'll now turn to Whitehead's theory on homotopy types of spaces, and we'll be looking at really very basic homotopy theory in this course. Really one-dimensional and enough about higher dimensions to say that a space is essentially one-dimensional and what we can say about it based on that. I mean, one-dimensional homotopic theoretic sense, not in the sense of being a graph which is too restrictive. Okay, so CW complexes is what we'll define here. So these are going to be defined inductively. CW stands for cell weak. Yes, we will see why when we look at the topology. It's an appropriate kind of weak topology based on cell maps. Okay, so minus one dimensional CW. We'll start with minus one dimensional CW complexes inductively, and there you have only one of them, which is the empty set. Okay. This might look a little strange. It's more conventional to start in zero dimensional, but this is nicer. It gives a clean inductive notion of homotopical dimension and so on, which is beyond this course, but still for this course it's nice to see. The justification for this is that if I look at a space, then its zeroth homotopy group is trivial if and only if it's the empty space. Okay. That's not quite the definition. What you want to say is that all homotopy groups starting with 0 are trivial if and only if the space is empty. We can't define that yet, but when we define that we'll see. So this justifies saying that there isn't even zero dimensional structure, so we give it a minus one dimension. Okay, so inductively we'll define n dimensional. So suppose xn minus 1 is a n minus 1 dimensional CW complex. Okay, so then an n dimensional CW complex, let's call it x upper n. Okay, well, it's any space is a space obtained by attaching so the way I've stated it, I don't want to fix xn minus 1. So by attaching a collection of n cells to xn minus 1 for some xn minus 1 as above. Okay. So recall the attaching is based has certain data. So the attaching is determined by certain maps. Okay, so they are determined by maps which are phi alpha. Okay, alpha in A, but let me call it an to start with, phi alpha, and where the maps phi alpha will map Sn minus 1 to in this case xn minus 1 to whatever space to which we are attaching it. So this is determined by these maps phi alpha. Alpha in an, I'm saying an is the index set for n, and we could even put an n here to emphasize this, which we will do for the other kinds of maps that we consider. But how about infinite dimensional? This seems too restrictive. We are talking only finite dimensional spaces. We do want to talk about infinite ones. It's quite important even for studying finite dimensional ones, as we will see. But so for that we can just take limits, namely, so let x1, let's say x0, x1, x2, etc., xn onwards be CW complexes, and xn is obtained from xn minus 1, okay, as above, by attaching n cells. So let me say as above. Then if I look at x, which is the direct limit of xn, is a CW complex. So this is again by definition. This is, we are taking two kinds of inductive constructions. One is just a step and the other is taking a limit. Okay. Okay, so an inductive construction and a limit. So by the way, xk in both cases is called a k skeleton. Is the k skeleton. Now just for consistency we should check a couple of things. So if we stop at finitely many stages, we can either think of the direct limit of a finite sequence or attaching only empty cells beyond that point. But since these are automatically inclusion maps that we have here, what will happen is that the final space will be the last space xn if you stop at finitely many points. So indeed, if you took limits, always you would get the same definition as you having separately for finite cases and infinite cases. Okay, so we have a notion of CW complex. We want to look at this both as a set and as a topological space a little more carefully, which is what we will do now in a way that is quite useful. So we look at it as a set and we look at it as a topological space. But first let's see some things more. Okay, this is not just as a set, but even from a topological point of view. We had these maps little phi alpha, okay, n, mapping Sn minus 1 to x. Here I've put dimensions everywhere to emphasize, and alpha is in the index set an. But we have along with these what are called characteristic maps, which is namely if we have a map, so recall that what we have is the set xn, which is attached, is xn minus 1 disjoint union with a bunch of cells. Namely, I look at alpha in an, I look at dn0. I can put an alpha to emphasize, but this is not the interior. That's not correct at all. Of course, it has to be the closed set. Okay, which, let me emphasize, this is the closed disk, if it's a disjoint union of these, divided by an equivalence relation. The equivalence relation comes from the maps little phi alpha. I won't recall the definition. What is important here is that we have inclusion maps. So we have phi alpha, which are inclusion maps. Now I'm going to write them as from dn, the disk, to the space x. Okay, and this is just d alpha n, but I'm emphasizing here that it's the standard space. So these are called characteristic maps. Okay, and what do we know as a set? So these are maps, they are continuous, so this involves the topology as well, but it will involve the topology in a stronger way in a moment. But as a set, we know two things. We know that phi alpha restricted to d naught is injective. In fact, it's a homeomorphism. But as a set, what we want to say is that it is injective. Okay, and secondly, every point is either in the image of this or it's in xn minus 1. Okay, and it's either in the image of the disk, it could be in the image of both, but then it's in the image of the boundary, so not in the interior. Okay, so hence as a set, x is going to be the disjoint union over all n greater than or equal to 0 and alpha in an of the image under the map alpha of the interior of this disk. And here I emphasize as a set. Okay, so every point is in the interior of a unique cell. This is a key property of cell complexes. And so we can also look at the topology now in terms of these characteristic maps phi alpha. Okay, we have already seen this with attaching maps. So it's simply a reformulation of a definition we had already seen. So this topology is the cell weak topology. And let's define it in two ways in terms of open sets. So let's say V contained in X is open if and only if the following holds. For all, well, n greater than or 0 and alpha in an, if I look at phi alpha inverse of V is open. Okay. If V is open, this being open is saying just that phi alphas are continuous. which they are under the attaching map. But the attaching map also has a weak topology. I mean, the topology of the space obtained by attaching also has the weak topology, in the sense that if it's also true that if a set is open, if and only if phi alpha inverse of V is open. So if the inverse image under each phi alpha is open, it follows that V is open. This is not continuity, it's a weak topology, and this can be formulated in a more categorical way. Namely, if I look at a function f from the space X we have just obtained, the CW complex, to any other space Y, this is continuous. Again, 1/2 is going to be continuity of phi alpha, if and only if I look at f composed with phi alpha. Now this is a map from Dn. I did not put an alpha to emphasize this is a standard space, Dn to Y. By the way, I'm sometimes using blackboard bold, sometimes not. There's no difference in meaning. So f composed with phi alpha, this is continuous. Again, for all n greater than or equal to 0 and alpha in an. Okay. So indeed we have a weak topology, in the sense that's a nice categorical definition. We should remind you of the coproduct. It is not the coproduct because the phi alphas don't have disjoint images. There's gluing on the boundary, but otherwise it's a coproduct like topology. Okay, so it's also injective or direct topology, or weak topology in the more old-fashioned way of viewing things. Okay, so indeed we can give a definition this way. So we can have an alternative definition of CW complexes. Alternative definition of a CW complexes is a space X, okay, together with, well, collections n greater than or equal to 0. We have sets an, and we have maps phi alpha mapping Dn to X, such that certain properties hold, such that we have this property, that is, the interior is a homeomorphism, or you could just take injective here. It will follow it's a homeomorphism from this. This property holds, such that, let me give them names, 1, 2, 3. Okay, 1, 2. And the third property, I'll point them to the more categorical version of the above equivalent properties. So if you have a CW complex, you can look at maps phi alpha. So you can think of it as a space together with maps from the disk. Each point is in the interior of, is in the image of the interior of a unique disk. So there it's a disjoint union of these. So each point is in a unique open cell. So it's made of these cells, and the topology comes in from the gluing maps, because we have let me write that more clearly. We have a maps not just on the open cells but on the closed cells, and the relations between these closed cells and the other ones will be as given. I might perhaps need to, let me just put a question mark. You can look at it. The fact that the boundary goes into the n-1 skeleton, I'm not sure if it's automatic or not. It's essential. Okay. So what I want to say is we can reverse this definition. So let me, instead of putting question mark, put an additional condition. Okay, that is how redundant it is, we can investigate, but it will not be important for us. So such that phi alpha of boundary Dn is, so if alpha is in An, then phi alpha is contained in the union of phi alpha. I shouldn't call this alpha, phi beta of Dn, and I could dk interior over k is strictly less than n, and beta is in ak. Okay, so it's contained in the boundary of that n cell is contained in the n-1 skeleton. You may need this as an additional condition, or from what we see later up to homotopy it may not matter. It's not central issue, so I won't address it here, but I don't want to make a wrong statement, so I'll clarify that you may need this condition as well. Okay, but what have we learned is CW complexes can be defined inductively. They are unions of cells, and their topology is given by saying characteristic maps are continuous, and that's all. Okay. So if composition with characteristic maps are continuous, then the function itself becomes continuous on the whole space.